Throughout the entire history of human civilization, we believed the universe was shaped by what our eyes could see. Light from distant stars, brilliant nebulae, exploding in colors, spiral galaxies turning like cosmic whirlpools in the endless dark. But everything we can see makes up only 5% of the universe. Imagine drifting through the infinite void. No gravity, no sound, no direction, only darkness. And within that darkness, trillions of galaxies glowing like floating islands of fire. Yet the longer you look, the more disturbing the truth becomes. All those galaxies are being held together by something completely invisible. Something like a colossal web made of unseen threads, pulling them, binding them, preventing them from tearing apart under their own insane rotation. What are those threads? Dark matter. A form of matter that gives off no light, no reflection, no color. It leaves no image on any camera, no trace on any optical sensor. And yet, without it, the universe as we know it would fall apart. Galaxies would disintegrate like fireworks. Stars would drift away from their orbits, like stones tossed by a giant hand. The most paradoxical thing is that while dark matter shapes the universe itself, it hides completely from human senses. We know it exists only because its gravity pulls on the things we can see. It is the shadow of gravity, the footprint of the invisible. And yet, in this darkness, humanity attempted something that sounds almost insane: to map the invisible, to draw a map of a structure no one has ever seen. No shape, no color, no visible signal. A task that should be impossible. But why insist on mapping it? Because without a map of dark matter, we will never understand the true structure of the cosmos. We would be like people staring at the surface of the ocean and believing the entire ocean is only what floats on top. The real structure of the universe lies beneath the light. Dark matter is the skeleton that holds everything together. The first clue arrived in 1933. Astronomer Fritz Zwicky examined the Coma galaxy cluster and discovered something outrageous. The galaxies inside were moving so fast that the cluster should have been ripped apart by Newtonian physics. Yet it wasn't. A massive unseen force was holding it together. Zwicky called it dark matter, though almost no one believed him at the time. 4 decades later, Vera Rubin reignited the mystery when she measured the rotation curve of the Andromeda galaxy. According to theory, stars farther from the center should rotate more slowly. But in reality, the speeds were almost identical, flat, unnatural, impossible, unless a huge amount of invisible mass enveloped the galaxy. Rubin was doubted, just like Zwicky. But her data was undeniable. Dark matter became a mandatory part of cosmology. Without it, every simulation of the universe collapses. But knowing it exists is only the beginning. The real question is, where is it? The structure of the universe, superclusters, galaxies, stars, planets, was shaped by the invisible framework of dark matter. Without mapping this framework, we cannot understand how the universe formed. We cannot explain why galaxies align into massive filaments, why vast empty voids exist, or why cosmic structures stretch across hundreds of millions of light years. So how do we see the unseen? The answer came from Einstein. Gravity bends light. When light from a distant galaxy passes through a region filled with dark matter, its path is bent slightly. Not by much, but enough for telescopes to notice. This effect is called gravitational lensing. By analyzing tiny distortions in the shapes of millions of galaxies, scientists can reverse engineer the distribution of dark matter in front of them, like observing ripples on water to infer the shape of a submerged object. We don't need to see dark matter directly. We only need to study its footprints on light. It is one of the most delicate and astonishing techniques humanity has ever created. And it allowed us, in the last decade, to begin drawing the largest dark matter maps ever made. The Dark Energy Survey, DES, analyzed more than 100 million galaxies. The result: a massive dark matter map covering 1/4 of the night sky. A breathtaking achievement. And when this map appeared, it revealed a cosmic web of dark matter stretching across space. Colossal filaments, dense nodes where galaxies cluster into superclusters, and enormous voids spanning tens of millions of light years. But the most shocking discovery wasn't the shape of the web, but its smoothness. The standard LCDM cosmological model predicts that dark matter should clump more strongly. Yet the real map shows it smoother than expected. This unexpected smoothness shook theoretical physics. Because if the map is right, the standard model might be wrong. And if the model is wrong, then our understanding of the universe's entire history, from its birth to its growth to the expansion driven by dark energy, must be reconsidered. New questions emerged with new anomalies. Some regions contain far less dark matter than expected. Others stretch out in unnatural, extended sheets or walls. These strange areas triggered 3 major hypotheses. First, gravity itself might behave differently on cosmic scales, meaning our understanding of gravity is incomplete. Second, dark matter might interact with itself in subtle ways we've never detected. Third, the LCDM model might be only a simplified version of something far more complex. The largest supercomputer simulations of the universe, like illustrious TNG and Millennium, recreate the cosmic web with astonishing detail. Yet when compared to the real map, they still mismatch by 10 to 20%. And within those small mismatches, the biggest secrets may be hiding. The future of dark matter research is now unfolding on an even grander scale. The European Euclid spacecraft is capturing data with unprecedented sharpness, scanning billions of galaxies to form a 3D map of the universe. Meanwhile, NASA's upcoming Roman telescope will allow humanity to see the evolution of dark matter across cosmic time. Not only where it is, but how it has changed over billions of years. This is no longer just a map, it is the diary of the universe. And then comes the most unsettling question of all. If dark matter is only the first invisible layer, how many more layers remain hidden? Thanks for watching. And see you on Podically Left It Is 9. If the dark matter map already disagrees with our standard models, must physics be rewritten from the ground up? In the darkness of the cosmos, an unseen structure holds everything in place. Without dark matter, galaxies would not exist. Without galaxies, stars would not exist. Without stars, Earth would never have formed. Life would never have appeared. Humanity would not be here. The maps we are drawing today are not just scientific achievements, they are reminders that we have barely scratched the surface of the truth. And when the dark matter map is finally complete, it may force us to rethink everything we have believed about the universe. The final question still hangs in the void. If dark matter is only the first invisible veil, what awaits behind the next one? Follow the channel for the next story.